In this video, we're going to talk about the mass and moment formulas for coil springs, wires, and thin rods, which may lie along this smooth curve C in space. So we previously defined all of these. We used triple integrals across a solid D in order to calculate them. So if we're dealing with a spring or a wire or any sort of thin rod which would lie on that curve, we can use a line integral with essentially the same formulas, just treating f as our density function, integrated with respect to arc length. Let's do a problem. In this example, we're going to find center of mass for a wire with a variable density defined as delta of t equals 3 square root of the quantity 5 plus t. And this thin wire lies along this curve in space, which is parametrized here. R of t equals t times the vector I plus 2t times the vector j plus 2/3 t to the 3/2 times the vector k. T is between 0 and 2. Now, in order to calculate center of mass, that means we need to calculate 4 integrals, one the mass, and each of these 3 first moments. So the function we're going to be integrating is the density function. And then, of course, we have to find our ds values for each of these. So I'll go ahead and do that first. ds is the square root of the derivative of t, we have 1 squared. The derivative of 2t gives me 2 squared. And the derivative of 2/3 t to the 3/2, that is t to the 1/2 squared, dt. Just to make sure we know where all of those derivatives that I took the square of, we had x equals t, y equals 2t, and z equals 2/3 t to the 3/2. So I'm going to simplify ds here, and I get the square root of 5 plus t. And of course, we've got our dt at the end. So to set up my line integral for mass, we know that mass is the line integral across C of the density with respect to arc length. In this situation, that's going to be from t equals 0 to t equals 2. My density function is 3 square root of 5 plus t, and ds, which we just found, is the square root of 5 plus t dt. And of course, this is going to be pretty easy for us to integrate. I'm going to find that my mass is 3 times the integral from 0 to 2. Root of 5 plus t times itself is just going to be 5 plus t dt, which is 3, 5t plus 1/2 t squared, evaluated from 2 to 0. Simplifying that, we get 36 represents our mass. Next, we need to find the first moment about each of the coordinate planes. And these are all relatively easy for us to integrate. So I'm mostly just going to focus on making sure we know the details of setting it up. And then I'm going to give you the integral value. So in order to find x bar is the moment about the yz plane divided by the mass. The equation for the moment about the yz plane is the line integral along C of x times density ds. So setting that up, we need to make sure we pay attention to, we have to plug in some parametric equation for x in terms of t. Remember that in this case, x is equal to t. So this is going to give me the integral from 0 to 2. I have t, then times my density function, 3 square root of 5 plus t times dt, which is the square root of 5 plus t dt. There's my setup. If I were to evaluate this, I would pull the 3 out in front. I'd have the integral from 0 to 2, 5 plus t. The root squared is just going to be 5 plus t, distributing the t. I have 5t plus t squared dt, which is 3 times 5 halves t squared plus 1/3 t squared, evaluated from 2 to 0. In this situation, I have 38. That means that x bar is 38 over 36, which simplifies to 19 over 18. So there's my x coordinate for the center of mass. Then let's do C. In order to find y bar, we need the moment around the xz plane divided by the mass. So the moment about the xz plane is the line integral across the curve C of y times the density function ds. So the only way this is different, when we set that up, we've got the integral from 0 to 2. What is my y function? Y is equal to 2t. So I'm going to have 2t times my density, which is 3 square root of 5 plus t, times ds, which is that radical 5 plus t dt. So simplifying this, we would have 6. The integral from 0 to 2. Again, we're going to have 5t plus t squared dt. That's going to be 6 times 5 half t squared plus 1/3 t cubed. Again, evaluated between 2 and 0. And that's just going to be double what we found for the last integral, 76. So y bar, the y coordinate for my center of mass, is going to be 76 over 36, which simplifies to 19 over 9. Right, we have one more calculation, and that will be z bar. And that's the moment about the xy plane divided by the mass. So calculating that moment about the xy plane, that's the line integral along the path C of z times the density ds, or the integral from 0 to 2 times my z function, which is 2/3 t to the 3 halves, times my density, which was given 3 times the square root of 5 plus t, times my ds I calculated, which is 5 plus t dt. So the 3's are going to cancel. I'm going to have a 2 in front. So this is 2, the integral from 0 to 2. And I'm going to have 5 t to the 3 halves plus t to the 5 halves as my function. I'll integrate that with respect or using the power rule again. So that gives me 144 root 2 over 7. Running out of space here. So when we go to calculate z bar, we're going to take this value, 144 root 2 over 7, divide it by that mass, which was 36. And we end up with 4 root 2 over 7. 4 root 2 over 7. So now I have my z bar, my y bar, and my x bar. So my ordered triple for the center of mass would be 19 over 18, 19 over 9, and 4 root 2 over 7. Ran out of space on the screen, so that's where we are, but That's it for this section. So again, we can use line integrals to find mass and moment formulas when we're dealing with a coil or a wire or some thin rod, all of which lie along that smooth curve C. And we can do it with a variable or a constant density.